I'm working as firmware development engineer at Nortek AS. Today, the topic of my presentation is reconfigurable ADCs for acoustic phased arrays. The plan for this presentation is that I will motivate a bit about reconfigurable ADCs and phased arrays, and I will introduce these two concepts. Afterwards, I will talk about time to digital converters, which are basically building blocks of reconfigurable ADCs. Then I will present the proposed solution we have implemented in these studies and some of the results. Finally, I will conclude my presentation. Starting with motivation and introduction. Nortek is a Norwegian company based in Oslo. We manufacture Doppler velocity logs, profilers, ADCPs, and other navigation solutions and other instruments to measure ocean currents, speeds, and velocities. The basic principle which our instruments are based on is Doppler shift or Doppler principle. Instrument transmits acoustic waves. These waves are reflected back to the instrument by the suspended particles inside the water, and our instruments measure the shift in Doppler frequency, and from that shift, speed or velocity is calculated. All of our currently available instruments are based on piston transducers. We can see example piston instrument in this slide as well. When we talk about phased arrays, they give us the opportunity of 3D imaging, beam steering, beam focusing, and other exciting opportunities. However, these advantages which we get with phased arrays come at a cost of the challenges, for example, exponential growth in electronics with the phased array. If we talk about a piston instrument, we have 3 to 5 instruments, transducers to process. However, in a phased array, we have n cross n. Let's say for a 10 element by 10 element array, we have 100 elements to process. So we see that the growth in electronics is exponential when we move from piston instrument to a phased array based instrument. In order to address this problem, we have some solutions. For example, row and column based addressing. Instead of addressing a single element, we can put elements in a row in series and columns in series. In this way, we get instead of n cross n, we get n plus n connections. For example, for a 10 cross 10 by 10 array, we get 20 connections. But still, it's a big number. The focus of this study was receiver chain and ADCs. Since we know that analog to digital converters are basic building blocks of receiver chain, so this study was focused on making a receiver chain with minimalistic external components or without using ADC chips, such that ADCs are implemented inside FPGAs, and this is the reason they are called reconfigurable ADCs. This reduces the cost of instrument, and it gives exciting opportunities to develop further the phased arrays. There are different flavors or different methods to implement reconfigurable ADCs, but we chose time to digital converters. Basically, a time to digital converter measures time between two events, let's say start and stop, very precisely down to nanosecond or sub-nanosecond resolution. In this figure, we see that we have a clock signal, we have an analog signal, and we have two defined voltage levels, V rise and V fall. So whenever the analog signal crosses let's say the voltage level V fall, we get an event which is called start event, and we start measuring time from start event until the clock edge, which basically is a stop event. The purpose of time to digital converter is to measure time between start and stop event very precisely down to, let's say, nanosecond. There are two implementations of time to digital converters. One is based on carry chain. We know that adders are basic building blocks of FPGAs. And in order to implement a time to digital converter, one can use, for example, carry units from adders. To implement a 10-bit TDC, we need 10 adders. So this, since adders or carry units have very small propagation delay, this means that this implementation gives very precise timing resolution for my TDC down to sub-nanosecond. However, the drawback is that much more resources are needed to implement, let's say, 10 or 12-bit TDC. The other method is based on multi-phase sampling clock. In this method, we divide a clock signal into sub regions. For example, let's say we have a 250 megahertz clock, which has a resolution of 4 nanosecond. If we divide this clock into 4 different phases from 0 to 90 degree, 90 to 180, 180 to 270, and 270 back to 360 or 0 degrees, we get 4 times improved resolution, that is 1 nanosecond. So we divide the clock into 4 regions or 4 sampling phases, and we use 2 counters, coarse and fine counters, to measure the time. This multi-phase sampling clock just needs 2 counters, not so many resources, but the drawback is that it gives moderate resolutions down to 1 nanosecond. However, some applications, for example ADC, 1 nanosecond time resolution is acceptable. And this is exactly what was done in this study using 250 megahertz clock, which is quite okay. We achieved a resolution of 1 nanosecond for our time to digital converter. In this slide, we see how a time to digital converter is used to make a reconfigurable ADC. So time to digital converter is implemented using multi-phase sampling and 2 counters inside FPGA. In addition, we have phased clock loop, which are again building blocks of FPGAs. They are used to generate, for example, clock signals, 250 megahertz clocks in this case. We see a ramp signal, which is called a reference ramp. So this reference ramp is generated by PLL and time to digital converter. It has same frequency as the clock of time to digital converter, and it is generated using 3R and C, which are external to FPGA. This reference ramp is compared with the incoming analog signals, and we used built-in LVDS receivers as comparator. So the output from this comparator acts as a start event for the time to digital converter, whereas the clock edge is used as a stop event. Basically, the reference ramp is fully resolved. It means that we know for every time step, we know the corresponding voltage. Since the time to digital converter gives the time between start and stop event, or the output when the output of a comparator is changing, from this time we can convert, for example, for each of the channel we can convert time to voltage, because the reference ramp is fully resolved and the values of voltages corresponding to times are saved inside lookup tables inside FPGAs. So in this way, with minimalistic external components, that is 3 resistors and 1 capacitor, we can make n-channel reconfigurable ADC inside an FPGA. Here we see the complete solution which we have tested in this study. It has basically 3 parts. The first is an acoustic array. In our case, it was a 28 by 28 array, but it was used in row and column based addressing. It means that it had 56 connections, 28 plus 28. The second part is isolation and voltage shifting. Since we have transmit and receive parts which differ in power levels, so we have to isolate electrically the transmitter and the receiver end. In addition, the array generates plus and minus voltages, both positive and negative voltages. However, FPGA only accepts the positive voltages at its input pins. It means that we have to translate voltages from minus values to plus values, and this was done by using, again, discrete components, resistors and capacitors. Finally, the output from voltage shifting block is fed directly to the FPGA or to the ADCs. We see that using minimalistic external components, we fed the signal from array directly to FPGA, where it is digitized by using ADC or TDC module and is available for further processing or calculation of velocities and speeds. Here we see results from our implementation. In the left figure, we see a 100 kilohertz sine wave. The output is for 4 channels, which are basically 4 ADC channels. The signal was generated using a function generator. We see that the input signal was changing between 1 and 2 volts, since, as I said before, the signal must lie inside. Must have positive voltage values. In the left right hand side, we see a Fourier transform for a signal from array. The array, which was developed at Nortek, has a center frequency of 479 kilohertz. This is the reason we see a peak around 500 kilohertz. The effective number of bits calculated from signal to noise ratio for this figure was roughly 7.18 bits. This 7.18 bits is much lesser than, for example, 12 or 14 bits used in piston-based transducer ADCs. However, we must remember that we have roughly 50 to 60 channels or 50 to 60 information sources compared to 3 to 5 for 5 information sources we have in a piston transducer. Basically, reduce ADC resolution is not a problem because we have so much a number of channels that it compensates for the loss in resolution of ADC. In conclusion, we can say that this study proved that the proof of concept is working, and in principle, it should be possible to use this principle in a commercial product. The benefits we get from this proof of concept is that it reduces the cost for phased array because 60 ADC chips is expensive to buy, of course, and they also need much more space compared to inbuilt FPGA-based ADCs. When it comes to array, we see that they offer improved form factor for an instrument. In addition, they offer the possibilities of 3D imaging, beam steering, beam focusing. Basically, it means that we can use a single instrument for various purposes if the instrument is based on a phased array transducer and phased array electronics. Finally, we tested this proof of concept for marine instruments or for our Nortek's instrument, but medical ultrasonic uses same kind of instruments but at different frequencies. The point is that this reconfigurable ADC principle should be usable in medical ultrasonics as well because um, it's the same instrument roughly. Thank you very much for your attention. Any questions?